Problem number 6. A ball rolls without slipping down a ramp, which turns horizontal at the bottom. At the bottom of the ramp, the ball falls through the air, as in the diagram. If the ball starts from the position marked O, it lands 10 centimeters away from the bottom of the ramp. Which starting position will get the ball to land closest to 25 centimeters away? Problem number 7. A mechanism consists of 3-point masses, each of mass m, connected by 2 massless rods of length L and a torsion spring acting as a hinge. The potential energy of the torsion spring is given by Us. This system is designed to walk down a set of stairs, as shown in the figure. The angles θ1 and θ2, see figure, represent the orientation of the rods, and their rates of change, ω1 and ω2, are the corresponding angular velocities. Assume that the mass on the surface is instantaneously at rest, which equation correctly describes the total energy of the system. Problem number 8. A symmetric spinning top, rotating clockwise at an angular frequency ω, is placed upright in the center of a frictionless circular plate. The plate then begins to rotate counterclockwise at a constant angular velocity ω. Assume the top's axis remains perfectly vertical and stable without any precession. From the perspective of an observer rotating with the plate, how does the top appear to rotate? Problem number 9. N circles in a plane, Ci each rotate with frequency ω relative to an inertial frame. The center of C1 is fixed in the inertial frame, and the center of Ci is fixed on Ci-1, for I equal 2, etc. till n, as shown in the figure. Each circle has radius Ri equals lambda Ri-1, where 0 less than lambda less than 1. A mass is fixed on Cn. The position of the mass, relative to the center of C1 is r as function of t. For the n equals 4 case shown, which of the following statements is true? During the time interval from 0 to 2 pi over ω, the magnitude of acceleration of mass on C4 is 1 of 5. The following information applies to problems 10 and 11. When two objects of very different masses collide, it is difficult to transfer a substantial fraction of the energy of one to the other. Consider two objects, of mass small m and big M much greater than small m. Problem 10. If the lighter object is initially at rest, and the heavier object collides elastically with it, what is the approximate maximum fraction of the heavier object's kinetic energy that could be transferred to the lighter object? Problem 11. Now suppose that instead, the heavier object is initially at rest, and the lighter object collides elastically with it. What is the approximate maximum fraction of the lighter object's kinetic energy that could be transferred to the heavier object?